So now we're going to talk about molecular speeds and see if we can relate the molecular speeds to certain properties exhibited by gases. Now, the first thing we should recognize, and this makes sense if you think about it, that if you have a gas, let's say you have a gas trapped in a container like a balloon or a beaker or something, then if you were to examine the individual speeds of the gas molecules, you'll know that not all of them will move at the same speed, right? There'll be a wide distribution of values when it comes to the speeds of the different molecules. So some will move at a slower speed, others will move at a higher speed, and there'll be some that will be, somewhere in between in terms of the speed. So therefore, what we do in this context, in order to get a representation of the average speeds of the molecule, is that we determine what is known as the root mean squared speed, right? Which is the square root of the average of the squares of the molecular speeds, right? So this is basically used as a proxy for expressing the speeds of the molecules, all right? And we can calculate it by using this equation right here. Now, the root mean squared speed by definition is the square root of the squares of the average of the squares of the speeds of the molecule. And we were introduced to this term in the previous video. Let me just remind you of what that is. That is equal to, let me put it up here since I have space up here. That will be equal to the square of the speed of molecule 1 plus the square of the speed of molecule 2 plus the square of the speed of molecule 3 plus the square, all the other molecule speeds up to the nth molecule, and then we divide all of that by n, all right? So that's what this part here means. And it turns out that we can calculate that by this equation right here. So the root mean squared speed would be equal to square root of 3RT over m, where m is the molar mass. Now, this is very important for you to pay attention to. M is equal to the molar mass expressed in kilograms per mole, right? So normally we would look at molar mass as being expressed in grams per mole. In this case, however, you have to express the molar mass in kilograms per mole, and I'm going to explain the reason why. And the R would be equal to 8.31 joules over mole Kelvin, all right? Now, we are accustomed to R being equal to 0.0821 liters atmospheres over mole Kelvin. They're both the same, but the difference, of course, would be the units, right? So where we have liters atmospheres here, instead we have the joule unit here. And that makes a difference in terms of the numerical value, right? So in this case here, where the units is liters atmospheres over mole Kelvin, R is equal to 0.0821 numerically, but if you're dealing with the units being expressed in joules per mole Kelvin, then R would be equal to 8.31 numerically. And this is the R value that is used in this equation right here, all right? Now, let me get out of this for the time being, and let me open up another PowerPoint slide, because I want to show you the reason why we express R and the molar mass as given, as I explained earlier. All right, so let me make this. Okay, so remember the equation is this. The root mean squared speed is equal to the square root, the square root of 3RT over m, the molar mass. Now what I'm going to do is, instead of putting numbers for RT and m, I'm going to put the units, and then you're going to see how the units work out for the root mean squared speed. We call this dimensional analysis, right? Now the 3 has no units, so I'm going to ignore that. R is equal to the units is joules per mole Kelvin, and T would be in Kelvin, and then we're going to divide this by the units of molar mass, which I said would be kilograms per mole, all right? Now, let me make this a bit more presentable. Let me erase this here so that I can put this under a proper square root sign. So please forgive my lack of writing skills. Okay, so that's the square root sign. All right, now let's see how we can work with these units. Now, the first thing I'm going to state here, which is something actually we're going to meet in the next chapter, but I'm just going to introduce it to you now. The joule unit. The joule unit is basically the same thing as kilograms meter squared over second squared, right? So what I'm going to do in the next line is replace the joule unit here with all of this right here, all right? So that would be, joule would be equal to, as I said before, kilogram meter squared over second squared. And then that would be divided by mole Kelvin times Kelvin divided by kilogram per mole. And again, all of this would be under the square root sign, all right? So let's see how this works out. Some things will cancel out. Some of the units will cancel out. Namely the Kelvin unit, I'm sorry. Also the kilogram unit here and here. And the mole units will cancel out here and here. So what are we left with? We're left with the square root of meter squared over second squared, which is equal to meters per second, which of course would be the units associated with the root mean squared speed. So what I'm showing you is the reason why the R units are expressed in joules per mole Kelvin, and the molar mass units are expressed in kilograms per mole in order for you to use this equation here. When you express the different values according to their correct units, as shown here, then ultimately what that means is that the root mean squared speed units end up being meters per second, all right? So I just thought it was important for me to show you why is it that we use those specific units when we're using that equation. Okay, so let me get out of this and go back to my slide presentation. Okay, so some comments about the root mean squared speed here. Typically, the speeds are quite high, on the order of 1,000 meters per second. So you might have, in some situations where the root mean squared speed is lower, maybe 900, 800, thereabouts, or you can have it higher, 1,100, 1,200, and so on, all right? The next statement here has to do with the relationship between the root mean squared speed and the molar mass. And if you look at this equation carefully, you'll see that the greater the molar mass of the molecules, the slower will be the root mean squared speed. So what that basically tells you is that the heavier molecules will move at a slower speed on average, provided that the temperature is the same, all right? Another thing I should point out here, which is not stated here, is that if you look at this equation, you'll see that as the temperature increases, the root mean squared speed increases, which makes sense if you think about it. When you increase the temperature, you're imparting more energy to the particles, and therefore they will move faster on average. So therefore, those are the relationships one can identify based on this equation for the root mean squared speed as it relates to the temperature and the molar mass, all right? So I want to show you this diagram, two graphs right here, which I think does an excellent job in terms of explaining the relationships I just talked about. Now, the one to the left is a plot of the relative number of molecules versus the root mean squared speed for different gases. Now, the pink line here is for oxygen. The green line here represents a distribution for methane. And this, I think it's purple line, represents a distribution of hydrogen, all right? So basically what each of these curves represent are the distribution of the gas molecule speeds at one temperature, which in this case is 273 Kelvin, all right? Now, in order for us to determine the root mean squared speed based on this graph, what you have to do is look at the maximum point of the plot and drop a vertical line down here such that it cuts the x-axis. Where it cuts the x-axis, that represents the root mean squared speed, all right, for the particular gas. Okay, so in the case of oxygen, we can estimate it based on where the perpendicular line will fall. If you start from the apex, and I'm going to try my best to make this as straight as possible. So it's going to cut the x-axis about here. So I would say my estimation is that, okay, this line here is 500. This is 1,000. So I would say this is about 400, give or take, meters per second, right? So that's the root mean squared speed for oxygen. In the case of methane, CH4, if I drop a vertical line down here, that looks like less than 1,000. I would say this is about 800 meters per second. And then in the case of hydrogen, well, this is easy because the apex is basically falling on this line here. So this line here cuts the x-axis at about 1,500 meters per second. All right. So basically what you'll find is that there's an increase in the root mean squared speed as you go from oxygen to methane to hydrogen. And that should come as no surprise because oxygen is the heaviest of the gas molecules. Its molar mass is about 32 grams per mole. Methane is the next in line in terms of molar mass size. This is about 12 plus 4, 16 grams per mole. And of course, hydrogen is about 2 grams per mole, right? So therefore, we see a pattern here. As the molar mass increases, the root mean squared speed increases from 400 in the case of oxygen to 800 in the case of methane, and then finally to 1,500 in the case of hydrogen, all right? So that's basically how the root mean squared speed varies with the molar mass. Now, the graph on the right shows you how the root mean squared speed varies with temperature for the same gas. So we're working with oxygen, right? And we're looking at the plots, the distribution at different temperatures, namely 273, 1,000 Kelvin, and 2,000 Kelvin, all right? And again, we get the root mean squared speed in the same way as we did in the graph on the left. We drop a vertical line. Well, we did this already for oxygen. The value here is about 400 meters per second. In the case of the same gas at 1,000 degrees, or 1,000 Kelvin, I should say, if I were to drop the vertical line down here, this looks like about 700, 600, let's say 600. This is all estimation, of course. And then in the case of 2,000 Kelvin, if I were to drop the vertical down here, this looks like about 1,400 meters per second. All right. So in this particular case, what do we notice? As the temperature increases from 273 to 1,000 to 2,000, the root mean squared speed, which is a proxy for the average speed, is increasing from 400 to 600 to 1,400 meters per second. So that shows you graphically, in this case, the relationship between the temperature of the gas and the root mean squared speed, which is to be expected. As the temperature increases, the average speed you'd expect to increase as well. All right? Okay, so we're going to stop here, and then we're going to spend some time talking about two terms. One is diffusion, and the other one is effusion. And in fact, we're going to spend more time talking about effusion than diffusion. All right, so that's for the next video. Until next time.